I'm from Auburn University. Today I'll be talking about some work I've done in collaboration with Cameron Seiler from the University of Oklahoma and Rafe Brown from the University of Kansas. Before I dive into that though, just a couple of notes. If you want to have a copy of these slides, they're right here. Just want to follow along or do whatever you want with them. They're there. And I just wanted to give a thanks to all the societies and all the organizers of the meetings. I don't know how you do it, but it's great work. So. All right. So I'll give you a pause for a moment to let people. So I learned about QR codes this morning from a much smarter PhD student and realized I probably should have done that. URL, but it's too late now. Okay. All right. So this is what Southeast Asia looks like today. Lots of islands. But not too long ago during the Pleistocene, during glacial periods when sea levels were much lower, it looked something much more like this. Right? So much more connectivity among the land masses across Southeast Asia. So the light gray is showing sort of land positive areas during glacial cycles. And then interglacials would come along and fragment that landscape into the islands that we see today. Okay? And so this is happening repeatedly throughout the Pleistocene glacial cycles. And so that raises an interesting question to biogeographers, and that is, did this sort of repeated fragmentation of the landscape sort of drive bivariant speciation and sort of create this species pump where the repeated fragmentation of this landscape was driving speciation? A very interesting question. If you want to see sort of a neat sort of animation, I think it's neat, animation of Southeast Asian sea levels over the past million years, if you have these slides, you can click that link or just hit that URL, and it sort of shows you the history through time. It's pretty interesting. I actually did it for fun and actually learned a lot doing it. So check that out if you're interested. So if we want to test sort of that hypothesis and sort of the species pump model, we need a prediction, right? So what sort of predictions does that model make? Well, let's use a cartoon example to get a grasp on that. So we can imagine that this is an island in the Philippines during a glacial period. An interglacial comes along and fragments that into two islands, and there's three lineages of lizards sort of evolving on that island. And so if that fragmentation event, that's sea level rises, causes them to diverge, what we should see is sort of temporal clustering of the divergences. And that's something we can get at, right? That's something that we can test. We can use genetic data to try to see if those times are clustered. So this is one possible scenario, but if we want to actually test this, we've got to consider other scenarios as well. So here's that scenario on the left here, so they all diverge at the same time. The other extreme is way over here on the right. They all diverge independently, or it could be something in between, right? Some of them co-diverge, but other ones don't. And so those are sort of the set of scenarios that we want to sort of get at. We want to test which one best explains the data, and we want to do that using genetic data. So how many divergence events were there? Sort of what taxon was assigned to which divergence event? That's sort of our goal here. So we've done this before with an approximate Bayesian computation approach that left us sort of unsatisfied in the sense that we didn't gain much information from the data. So approximate Bayesian world, you got to reduce your data into summary statistics. After we did that, we couldn't say too much. And so, for example, over here is a result from 9 pairs of populations of different vertebrates on the islands of Negros and Panay in the Philippines. Okay, and those were islands that were connected during glacial cycles. And so what we're looking at here is they could all share the same divergence event here on the x-axis. They could all be independent, or they could be somewhere in between. So this is a number of divergence events sort of explaining those. The light gray bars is the prior probability distribution of those scenarios, and the dark gray is the posterior, right? They look very similar, right? And so our data aren't saying very much. That's where we sort of left off, and we're sort of figuring out what do we do next. Data aren't telling us much in this approximate Bayesian framework and with the data that we have. So 2 possibilities. We either need to get more data, so more information, or a method that better uses information and data, right? So a more efficient method. So we decided to do both. Why pick one? We can try both. So first I'll talk about sort of the more data approach, and then we'll talk about the sort of more efficient method. So for the more data, we decided to focus on 2 radiations of geckonid lizards in the Philippines. The genus Cerdodactylus over here, and the genus gecko over here. Sort of widespread across the Philippines. The relative specios seemed like a good group to use for this. Plus they're cool. So they got that going too. So what we did is we sampled for both genera 8 pairs of populations from across the Philippines. And what you see in purple and sort of this bluish color are pairs of islands that were either connected or almost connected during the glacial periods. Okay? And in these yellow ones are pairs of islands that were never connected. These are oceanic islands that were never even close to each other, no land bridges. And so those are sort of controls. If we start seeing cluster divergence times with those, we know our method is not working. Right? So those are sort of a sanity check. All right, and we collected our rad-seq data from all of these. So a bunch of high throughput sequencing. All right, and so the new method that we developed is called eco-evolity, and it's going to do this in a full likelihood Bayesian framework. So using all of the information in those genomic data, can we do a better job of sort of estimating shared divergence times? A little bit about this method. It uses this really elegant mathematical work by David Bryant and colleagues from 2012 to analytically integrate over all the possible sort of coalescent gene trees and mutational histories along those gene trees while you're calculating the likelihood. So you don't have to deal with that numerically, it's all taken out in the likelihood calculation. So it's very efficient. And then we use a Dirichlet process prior over all those possible scenarios that we have to consider. All right, so the goal is an efficient method, one that's full likelihood, so using all the information in the data, and that can handle genomic data in a reasonable amount of time. So that's the hope. And we simulated a bunch of data sets that look exactly like our Gekana data sets, same number of loci, same length of loci, same missing data and all that. Then we analyzed that with eco-evolity just to get a sense of how well it's behaving when we know the truth. All right, if you want to learn more about these sorts of methods, check out my PhD student Carrie Cobb's poster tonight. He'll be talking a little bit about this, and then also I'll be at the Software Bazaar hanging out, so anybody that's interested in these methods can come chat with me. Happy to chat. Okay, so let's look at those simulation results first. So we're not looking at real biological data yet, we simulated these rad-seq data sets and we estimated them. So we know the true time of divergence for the 8 pairs of Cerdidactylus and the 8 pairs of geckos, and we're trying to estimate those. And we seem to be doing a pretty good job, right? What we want is things falling along this 1-to-1 line. Things look pretty accurate. Pretty happy with that. But what about sort of differentiating between those scenarios of divergence, right? The models, the number of events. So this is the true number of events for the 2 different data sets, and this is the estimated. And so once again, so the number in these squares represents the number of simulations that sort of falls within that bin. And the darker color is a higher number. And so we want to see high numbers along that 1-to-1 line. And we're doing pretty well. I'm pretty happy with that we're able to sort of get the right number of divergence events that sort of best explains the variation in the simulated data. All right, so now what happens when we actually apply this to the real data? Oh, sorry. Yep, seems to be doing well with the simulated data. All right, so let's look at Cerdidactylus first, the good old bent-toed geckos. So here we have, right, once again, the number of divergence events down here. The dark gray is the posterior support, the light gray is the prior support. So we're seeing strong posterior support for 8 divergence events. And there's 8 pairs, so that means no co-divergence, right? They're diverging independently. And then here's the posterior distribution of those divergence times, if you're interested in what those look like. So we've got pretty precise estimates, and they're not sort of overlapping. I had to remove one because it's much older than the others, and you couldn't see the other ones. Anyway, so if you're a fast counter, you'll see that there's actually 7 peaks, not 8. That's one. All right, so strong support for independent divergences with Cerdidactylus. All right, so what about gecko? Very similar pattern. So not as strong, but still the highest posterior support for 8 divergence events. So there's 8 pairs, so no co-divergence, right? So it's independent divergences. And there's the posterior distributions of the times of the 8 pairs from the various islands. And it looks like there might be something interesting going on right here. And your eye is kind of drawn to that, right? Oh, these things look like they may be codivergent. But what you have to do as a Bayesian is say, well, what's the prior probability of that and what's the posterior probability of that? And the prior probability of that is actually a little bit higher than the posterior probability. So the data are actually telling us it's less likely than we sort of expected before we looked at the data that they codiverged. And so the data are sort of telling us that they didn't, if that makes sense. Right, so weak support for independent divergences with gecko. All right, so just a few take-home points here. There is support against the species pump hypothesis for these lizards on these islands. We're not seeing these sort of temporally clustered divergences that are predicted by that hypothesis. And sort of our alternative hypothesis to sort of explain that is for these lizards, sort of the habitat heterogeneity within these islands is probably much more important than whether the islands were connected by like a beach for a couple thousand years or tens of thousands of years, right? And so these things occur on rocky outcrops, karst formations, forests. And so whether or not two islands were connected by habitat that perhaps was unsuitable might not matter to these geckos, right? In fact, they might actually be more likely to get from one island to another if there's water there. Because they're probably not likely to venture out into habitat that they're, that they don't like. But if a typhoon comes by and washes a bunch of vegetation into the ocean, they can raft on that vegetation to another island. So they might actually be more likely to move among islands when the water's there than when the land's there. At least that's a post hoc explanation for everything. All right, so some caveats to think about. So we need more pairs, right? So these glacial cycles were repeated, and we only have about a handful of pairs from each of the genera. Right, so we could just have gotten unlucky. We didn't sample enough pairs to start seeing co-divergences, right? They could have diverged at different interglacial periods, for example. So we need more data would be helpful. It always is. There's also these pairs of populations that we looked at are on different pairs of islands that would have fragmented during sea level rise at different times, right? And so, okay, I need to wrap it up. And so there's variation in that. So what we did is we looked at bathymetry data and sea level projections back in time and tried to get an idea of how much variation there would be in when these islands diverged. Probably about 3,000 years are kind of the upper limits of the variation and when they would have been fragmented. And then we looked at sort of the maximum resolution that we could get out of equality with these data. And there doesn't seem to be any way that we would be able to detect divergence times that were only a few thousand years apart. So not a likely explanation for what we saw. This one's the most important one. So we're assuming they all have the same mutation rate. Our results are only as good as that assumption. We analyzed the two genera separately for that reason. They're all closely related populations with very similar life histories. So our hope is that they have similar mutation rates, but that's an assumption. If that's violated, so all bets are off, right? And that's why we're working on fully phylogenetic ways of getting at this question, so that we can actually learn something about relative mutation rates while we're doing the testing. All right, but in our opinion, it seems safe to conclude that at least that species pump model is not the norm. It's not the rule for these populations of geckos on these islands. Maybe it's an exception. Everything is up on GitHub, the software, open science notebooks. You can check that out. And lots of people to thank. I had great review experience on both papers through both SSE and SSB. So a big shout out to the editors and the reviewers. Did excellent critical feedback. And lots of people to thank. And without further ado, I'm happy to take questions. Ellie, you were first.
So geckos are notoriously great dispersers. Do you think you'd see something different if you looked at taxa that didn't raft over water so long?
Yeah, so that's a very good point. So certainly we expect ecology to matter. So the dispersal abilities of these taxa are going to be very relevant. And so if you look at birds, for example, or bats, it's going to be very different than you look at lizards or something that's even as less dispersed. Yeah, amphibians, exactly.
Sulawesi is an island that has coalesced from many separate islands. Are there islands in the Philippines that may have experienced a similar geographic history?
Absolutely, yeah. So some of the current islands are sort of paleo islands that merge together. Yeah.
And that would have happened
older time scale.
Older time scale.
Yeah, so tens of millions of years rather than sort of hundreds of thousands.
Sure.
Any other questions? Thanks.